Good afternoon. My name is Lieutenant Commander Robert Gilpin, and I'm a researcher at the Royal Military College of Canada. I'm a naval officer, and today we'll be presenting multiple input, multiple output radar design using software-defined radio. The supervisors for my research are Dr. Hefnaoui and Dr. Bray, both professors at the Royal Military College. To start, we'll just briefly discuss radar in general. So as you can see in the GIF below, there is an antenna which we'll call our radar. What it does is you'll see the blue energy pulse leave the radar antenna. It travels out and hits a target, in this case an aircraft, reflects off the target, and some of that energy is bounced back and received at the antenna. In the bottom right, with the green background, it has a display of the wave traveling out, hitting the target, and then that energy being received as a small blip at the end. One thing I will note is that digital radars perform their signal processing on a number of pulses. So it sends out a number of waveforms, receives all that energy, and then performs processing on those. So as I alluded to, that processing usually is performed on what we call the radar data cube. So the data cube is a collection of samples that the ADC creates from the return energy. So the first portion we'll look at is the return of a single antenna. And so the first diagram on the left shows the samples going into the page, and that's what we call fast time. So each pulse returns one row going into the page, and then multiple pulses are collected. In this case, there are 12, and then the pulses are called slow time. So each antenna in the radar, in radar case, there are often several antennas, produce a slice of the radar cube like this. In the second picture, we can see that the first antenna is red, and then the second antenna in green, and again, both in fast and slow time. After all of the antennas, which collect their samples at the same time, we layer those samples on top of each other to create what we call the radar data cube, with fast time going into the page, slow time going across the page, and then the spatial domain, or each antenna, going down through the page. So in this case, we perform the most basic signal processing that our radar performs, which is using the fast Fourier transform. So in this case, we perform 3D FFT first in fast time for range, then in slow time to calculate the velocity, and then in the spatial domain to provide bearing. And then finally, we display that information. So the reason we're doing this research is because traditional radar systems are built using dedicated hardware. And that's because the signal processing required to keep them real time is extreme. And also, the radio frequency used are often very high frequency and require dedicated hardware as well. So radars on board a military platform, be it a ship, aircraft, or land vehicle, need to perform a number of different missions. Some of those missions would include search radar, long range, short range, navigation, and fire control for weapon systems. So in addition to the radars, there's also other equipment that requires RF capable processing, and they are all located on the upper decks of the ship, of course, or airframe or vehicle. So what I've done to show you how much real estate gets taken up by radio frequency equipment, I've shown a Flight 2A Arleigh class destroyer on the right of the page. And as you can see, all of those sensors take up a lot of the room on board a ship, and it also creates a lot of weight for the ship. The solution, the software-defined radio. So what the software-defined radio hopes to do is to replace a lot of that equipment below decks in order to do the job of multiple systems in one. So the benefits of the SDR is that the signal generation, filtering, mixing, and almost all of the DSP is done through software. So there's no actual hardware requirement, making them very flexible. They're also flexible with their RF front ends, as they're able to produce a very wide range of frequencies, and their instantaneous bandwidth is often quite high. So the software-defined radar research goals for our team at RMC is to study the advanced technique called multiple input, multiple output radar. To do that, we've purchased 4 software-defined radios from Ettus Research, an N321, which provides the local oscillator signal, and 3 N320s in order to produce an 8x8 or a 64-channel MIMO radar using a host processor for the DSP. Some of the follow-on projects that we're looking to do is accelerate the DSP by using hardware, namely the FPGA on board the radios, and then potentially the graphics processor unit or GPU on a host computer to accelerate that processing. Just to give a quick overview of what the actual radar looks like in a high-level sense, is that we have the SDR in this N321, N320 box here, where it has the RF front ends, the FPGA, which communicates to a host processor. Once that data is passed to the host processor, we're using GNU radio software in order to perform the DSP, that 3D FFT we talked about, and then pass it to a human-machine interface. Interesting, C++ is used to communicate with the radios in our case. It has Universal Software Radio Peripheral Hardware Driver, or UHD, which is essentially a C++ library we can use to conduct whatever waveform measurements we would like, or get the radios to perform how we want them to experience different techniques of radar. Some of the difficulties we've run into is we've run into buffer overruns. So the data rate from the radar comes in at 1 or 10 gigahertz. And during operation, if we just turn on the tap and let the radio produce as much information or data as possible, it just overruns the buffers. So what we've done is we've implemented a timeout in between radar data cubes in order to allow those buffers to clear. We're also having some problems with burst transmission using the radios, and I actually think that's a problem with UHD communicating with the radios itself. So we're in the process of investigating how we can actually make the radios sleep while the information is processed and then turn back on to send out the next burst of radar signals. And then the last piece that still needs to be answered is we're uncertain exactly how the electromagnetic wave will interact with the environment if we use code division. So if we change the phase but use the same frequency in order to achieve orthogonality of our waveform, we're wondering if what nulls will be created in space. So that requires further investigation. So that's it for me, Lieutenant Commander Gilpin at the Royal Military College. If you have any questions or would like to get in touch, please go ahead and email me on the screen below. Thanks. Bye-bye.